So this is the 2018 um, constructed response question, right? Starting with question one. And then, in terms of the format, this sticks to our typical AP format where basically there are three questions that are 13 minutes each and then two questions that are 25. In today's lesson, we're going to go over one that gives us about 13 minutes and then one question that's going to supposedly take about 25. Now, keep in mind, it might take us a little bit longer to work through these, just as, our live lecture, I'm going to be explaining different parts and I'm not going to be working it through as though I'm a student just trying to rush it out. I'm going to try and thoroughly explain. So feel free at any point to kind of stop me with this. Yeah, we did have a quiz on this. You're right, Alexia. Um, so maybe with this question, then I'll move a little quicker if people remember it, but maybe it doesn't hurt to go back over. Um, but it says a spacecraft of mass m is in a clockwise circular orbit of radius r around the Earth, as shown in the figure above. The mass of the Earth is me. It says for part A, in the figure below, draw and label the forces, not components, that act on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. So if we are in a circular orbit around Earth in our spacecraft, um, does it give us any more information? No, it just says that we're in orbit. It doesn't say that we're using any sort of thrusters. It doesn't say that we're kind of keeping ourselves there in any way. And as you guys may know, um, once we typically send an object into orbit, there doesn't need to be any action force of thrust to keep us there. Because what force will constantly act on us as we move in an orbital path? Yeah, FG, or force of gravity, right? And that force of gravity will point us towards Earth, right? That'd be FG. And technically speaking, that force of gravity would also act on Earth pointing towards the spacecraft, right? Remember, whoops, on the figure below, probably draw it here, right? But right along this dashed line is where we should draw our FG. Now, it doesn't really matter how long we make this arrow because we're not really drawing it to kind of scale or anything like that. It just says to make a distinct dot and show our arrow pointing away from the spacecraft. So as a result, we know that our force of gravity can kind of keep us in this motion. But what type of motion is this? If we're moving in a circular orbit, we could consider this a centripetal motion. So one thing that you might recall, just as we think of this, right? And this is going to be kind of where we'll get into our next part here. But just remember that Fg is the same as our centripetal force in this instance, right? If we're moving in a constant circular path, right, we can relate those two. So now for part I, it says derive an equation for the orbital period in terms of m, me, r, and physical constants. Guys, when they say physical constants, I just want you to know that that really refers to um, any any constant that we're given on our reference sheet, as well as just kind of any like known value. So, for example, the acceleration due to gravity near the surface of Earth is 9.8 meters per second squared. We denoted that by little g. Little g is a physical constant. And then it says, if you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure from part A. So realize, guys, I'm going to do part I down here because I didn't really give enough space when I was pasting this over because the document didn't actually have that space built in. So I'm going to solve part I right here. So for part I, or BI rather, we want to find our period. But what is our period really? Our period is the length of time that it takes to go one full lap, right, or one full circumference in this case, right? Um, so when we think about relating our orbital period in terms of mass, me, and r, we might want to start thinking about how we can talk about, or rather, how we can relate the orbital period to the centripetal motion, right? And the first thing that I would want to do, I think, to get to there would be to say that, as I said before, Fg is equal to Fc, right? But when we talk about Fg is really G, me, whoops, m, all over capital R squared, right? g m1 m2 all over r squared. I'm just using the physical constants that we highlighted here in teal, right? The ones that we were mentioned within the problem. Then we know that fc is really just little m times v squared over r. Now, when we do this, I actually want to solve this for v squared because just as a little aside here, right? Velocity has baked into it a unit of time. If you remember, when we talk about a speed or a velocity, right, it was typically a distance over a time, t. But if we talk about this velocity, right, we can say that this velocity is relative to its centripetal orbit in that we can say that, if we consider the distance to be 2 pi r, or the circumference of our orbit, then our time becomes our period t. And I can set this equal to our orbital velocity speed there, right? Because by definition, if our centripetal orbit speed has to be fast enough to keep us in this motion, then it would have to be relative to um, our orbital velocity there, right? So as a result, I can kind of establish this such that I can solve my equation for t, right? Um, Now, if you remember, what we're really denoting here is we're trying to figure out our v orbital, and really then we're taking our v orbital and we're then relating it to that our v orbital is really going to be equal to, we want to find our period, right? It's really equal to 2 pi r over t. That's another way to think of it. So you could just solve for v first, or you can substitute in whatever's easiest for you. I think here it might be easiest to first find our orbital velocity, and that's what we're doing by denoting these two equations here. So solving this for orbital velocity, our r and one of our r squared values will cancel, and then our m and our m value will cancel, such that v orbital is really equal to the square root of g m e over r. So if that's my orbital velocity, and we said that our orbital velocity is simply 2 pi r over t, well, then I can solve for my period t by just rearranging and solving this, right? By multiplying across. So t becomes, right, if I substitute this in, I say that 2 pi r over t is equal to the square root of gme over r. Then t, if I kind of move things over, t is equal to 2 pi r over the square root of gme over r. Now, um, technically speaking, right, we don't really have to simplify that any further, um, because really, we have an expression now that's solved for t in terms of our physical constant, right? So we would say that that's really our final answer there. It's ugly, but it works. It then says for part I, or double I here, or part two of B, right? It says the second spacecraft of mass 2m is placed in a circular orbit at the same radius r. Is the orbital period of the spacecraft greater than, less than, or equal to the orbital period of the first spacecraft? So then I encourage that you look at this equation that we just derived. Is mass even playing a factor here? Is there any mass in our orbital period equation that we just derived here? I guess there's a mass, right? The mass of the Earth. But is the spacecraft's mass here? No, right? So as a result, this must then be equal to. Now, briefly explain your reasoning. You can reference your equation. As seen in the equation that we derived, t is equal to 2 pi r over square root of g me over r. The mass of the spacecraft does not affect the period, the orbital period, right? Um, so what would I say? Uh, there's my brief explanation, right? Let me just squeeze it down here. The mass, oh, why is it not letting me write? Uh-oh. Oh, there we go. The mass, of the spacecraft. Wow, I can't write it all towards the bottom here. This is like, looks like a third grader's handwriting. The mass of the spacecraft does not affect the orbital period. And then what you could just put in like parentheses here is t is equal to 2 pi r over square root of g m. Oh, it's not going to let me write that. Darn it. Square root of g m e over r. Yeah. Basically just referencing the formula. I know that was like very horribly written in my third grade handwriting. It's just towards the bottom of the page. If I put my palm on my tablet, it doesn't read my pen strokes. So that's why I had to write like a third grader. Sorry. But you guys get the idea. Then in part C, it says the first spacecraft moved into a new circular orbit that has a radius greater than r, as shown in the figure below. It says, is the speed of the spacecraft in its new orbit greater than, less than, or equal to the original speed? What I recommend for this is to look at our V orbital equation that we first derived, and it was right here in purple. We said that V orbital, in order to maintain the orbit, right, is equal to the square root of gme over r. So what it's saying here is if we now have an orbital radius greater than r, will our orbital speed have to increase, decrease, or stay the same as compared to the original speed? What would we say here? What type of relationship is this where one variable is in the top of the kind of the numerator here and the other one's in the bottom, right? Basically, this is an inverse relationship, right? So as a result, your orbital velocity will decrease, meaning that the further away you are, and think about it in terms of forces, right? If gravity is your centripetal force, gravity is going to be pulling on you with a weaker amount, right? It's going to be less forceful the further out you go, which means that to maintain an orbit further away, you actually need less speed than to maintain an orbit close to Earth. So we'll say that it is less than, right? And as seen by the orbital is equal to the square root of gme over r, to maintain an orbit further from Earth requires a smaller velocity, orbital velocity. Now, if we wanted to go into this a little bit further, we could even really state this is because our centripetal force decreases as we get further from Earth, right? This is because our centripetal force, and I might even put in parentheses, the force of gravity, decreases as we move further from Earth. Now, the reason why I put that extra little bit is it just shows like full understanding. Now, I'm sure that first statement would be enough by the fact that it says briefly explain, but it's always, it's always helpful to give a thorough explanation, even if it asks for just a brief explanation. Now, if you noticed, time-wise, I didn't really get a timestamp on that, but I'm pretty sure we spent about 15 minutes going through this, which isn't bad. Let's move on to our next question, though, if there's no questions. Oh, whoops. Next question's on another doc. Wrong one. Here we go. Guys, for our next question, we're going to be looking, whoops. We're going to be looking at, press the plus sign. There we go. Actually, I can just scratch it with my finger. That's easier. We're going to be looking at a circuit question. And I'll tell you right now, I distinctly remember when my students took this question. They didn't really, one student in particular was very upset about this question. I don't know if you guys knew Braden Nana. He was a valedictorian. But anyway, He he hated this conductive dough question, which is kind of funny to me. But regardless, it says a group of students prepare a large. No, it wasn't that he just disliked the question. He actually ended up scoring quite well in the exam. Um, uh, FERPA says I can't really tell you his score, but he did pass. That might be lying. That might be saying too much. But that's okay. It says a group of students prepare a large batch of conductive dough, a soft substance that can conduct electricity, and then mold the dough into several cylinders with various cross-sectional areas A and lengths L. Each student applies a potential difference, delta V, across the ends of the cylinder and determines the resistance R of the cylinder. The results of their experiments are shown in the table below. Okay. It says the students want to determine the resistivity of the dough cylinders. I'm actually going to stop right there. When I say I want to determine the resistivity, what's the first thing that we should think about here? We should probably jump to thinking about our equation for resistivity. Now, by the fact that you see A and L, that should already be a hint here, right? Um, so resistivity, careful, resistance, right, is measured in ohms. Now, this is something that we got to in circuits. I know this is a circuits question. I'm still going to go through it, even though technically this is not covered on this year's exam, because the process of solving the AP question is still important. And there's still some good skills to be learned. But it says R is equal to rho L over A. This is our equation for the resistivity of a material, rather, a resistance of a material, where rho stands for resistivity. So this is really the part right here. This is really what we're looking for. So what measurements were made here? Well, L, A, and R, right? And it says indicate the quantities below, which could be graphed in order to determine the value of the resistivity of the dough cylinders. You may use the remaining columns in the table above as needed to record any quantities, including units that are not already in the table. So right now, what is in the table that you would need? Well, if we were to try and figure this out, right, what would we want to graph? What would we like kind of need to graph to find resistivity? What would be an easy way to make this into like intent a linear relationship? What is a linear relationship? Y is equal to mx plus b. Hint, in all of physics, we usually find specific values from a graph the same way. What do we usually analyze to find the value from a graph in our introductory physics course? Slope, right? So if we're looking for resistivity, we want resistivity to be the slope. How can I do that? How can I do that? Well, if you notice in our parallel here, we can make R our y-axis, right? We can make R what we graph on our y-axis because, yeah, R is a function of I or L over A. I actually really like that because then our slope remains, rho, right? And then our x variable actually becomes just L over A. Now, L over A has to correspond to a specific data point. So this is where it says, we can make an additional spot in our data table, right? To help ourselves out. Now, what is L over A really measured in? Well, it's meters over meters squared, or simply units of 1 over meters. Or sometimes we would write that as meters to the minus 1, right? And I think I would definitely add this to our table. Um, Wait, what's A over L? Hmm? I'm confused. Or are we just backtracking a little bit? Sorry, I read that a little late. Um, but in terms of this, right, we want to now calculate each of these values from our data over here. And this is where, you could just take out a calculator and then fill out this data table. So I'm going to go through and do this, right? But if we do 0.03 divided by 0.00049, we'll get an answer of, it's kind of big. It's 61.2. 61.2. And I'm going to go to roughly 3 sig figs here. Technically, I only have to go to 2 significant figures if we're really following our sig fig rules, because we're dividing numbers, right? Now, the AP I've never seen be a stickler for sig figs in recent years. That's been off of this from a while. So you just move over A so that it would be R times. No, we're not gonna solve for resistivity directly because we're gonna find it from the slope, Jonathan. That's a good question. He was saying, wait a second, can't we rearrange the equation to find rho is equal to R times A over L? But careful, we want to find it graphically. So we'd like to keep things kind of as terms of an x variable multiplied by the slope is equal to the y variable. So we're gonna actually find this from the graph. We're gonna find the slope of the graph to be rho. So in going through this, continuing through, right? I guess technically I could have rounded that to 61, but I'm not. Maybe we should. Maybe we should stick to 2 sig figs. That might make our life easier, actually. Now, why would I do 2 sig figs? Just to kind of go over this, right? Remember Pacific present rule. In terms of these two numbers that we have, the 0.00049 and 0.030 are both in 2 significant figures. So if I divide the two, you stick with the least precise value, which is still 2 sig figs. So for the next one there, we have 0.00049 divided by, or rather, whoops, I did that backwards. 0.050 divided by 0.00049. And this is 102. Ooh, I just figured out an issue with this. Kind of. Ooh, what's wrong about this whole thing? We notice that, what are we doing actually here? We're applying different voltages. Should that matter? Actually, no, because that'll be accounted for in the fact that the resistance is different. No, we're good. We're good. Sorry. Yeah, I was just looking at this and I was like, wait a second. This is the same cross-sectional area and the same length, but it has a different voltage. Why should that not concern you? Well, remember, R is equal to V over I. So basically, by having a different voltage means a different current will run through it, which will then affect our resistance value. And that's why this resistance does not equal the other resistance up here, even though they have the same area and length measure. So continuing through with this then, so 0.080 divided by, actually, what did I just mess up? If I said I was going to stay consistent to my significant figures, I just screwed it up completely, right? Because technically that wouldn't be 102. What would I have to round that to? This would just be 100. If I was going to stay, or actually, that's still not 2 significant figures. Uh-oh. How do I fix this, right? How do I make 102 2 sig figs? If I really wanted to do that. Not that they're asking you to do this, guys. So if you were struggling with that, you could just keep it as 102. No, you wouldn't round it up to 110. You still have to round appropriately. This is one of those weird rules, right? So it'd have to round down to 100, but it'd have to be, yeah, it is a scientific notation. It has to be 1.0 times 10 to the second. As weird as that sounds. Now, why is it 1.0? Because all digits in front of the scientific notation are significant. So it's really still 100 is basically what I'm saying, but it's just being a little bit more precise. And if I go to the 0.080 divided by 0.00053, this gets me 150.9, which we would just round to 150 without a decimal at the end. And then we have 0.15 divided by 0.00057, which gets me 263, which I would then round down to 260. Now, I kept everything to 2 sig figs mainly because I thought it would make my graphing easier. I don't know if it actually will, but realize that as long as you stay consistent, it shouldn't matter whether or not you keep it to sig figs or place value. Just make sure your data is at least in some way consistent. I think often in going through data tables, it's good to keep everything to the same place value as opposed to necessarily the same sig figs. So if I decided to go out to the 10th place, I would probably go out to the 10th place for every measurement. But that's okay. I kept it with sig figs. So in doing this, our vertical axis, remember, is our R value, right? We said that over here. And then our horizontal axis is going to be L over A, right? And then when we do this, right, we're going to, on the grid below, we're going to have to now actually plot this, right? And if you look, each one of these is 1, 2, 3, 4. So they're smaller bubbles. There's 5 divisions in each one of these larger, darker squares, right? So now I need to come up with a solution here when I realize that this is 1, 2, 3, 4, 5, 6. So there's effectively 30 divisions, and this is 1, 2, 3, 4, 5. So that's 25 divisions on the 2 respective axes. So if I get up to a maximum resistance of 105 and I have 25 divisions, so if I do 105 divided by 25 divisions, it would be about 4.2 per division, but that's not enough. So I'll probably do each division as roughly 5. And that way that'll get me up to 125, right? So rather than labeling every division though, maybe I'll just label every 5 divisions, right? So this will be 25 ohms. This is resistance, whoops, measured in ohms. And yes, I tilted my head to do that. And then our next one here is 50 ohms, then 75 ohms, 100 ohms, and 125. For my other axis, realize it goes up till 260 in roughly 30 divisions. So I'll take 260, I'll divide it by 30, and I get about 8.66. That's not going to be fun to work with. Let's go by tens. So then if this is 10 every time, this would be 50. And now, careful. So for our units, this is going to be length divided by cross-sectional area. Which is measured in units of meters to the -1, or 1 over meters. Now, technically speaking, I know I kind of was redundant here for the y-axis where I labeled ohms after each thing. Because my units are right here, I don't really have to label the units on each division. Like this is excessive. I don't actually have to label this m to the -1. And maybe to clean this up, I'll actually get rid of those units because I kind of labeled the axis. There's no need. So then this would be 50, 100, 150, 200, 250, 300. Okay. Then for our next step here, we want to actually go ahead and plot these points. So just kind of going through, I have 23.661. I'm going to sketch this roughly, guys. I'm going to try and do this as quick as I can. But 23.6 and 61. So 61 would be roughly like right past this line. And what was it? Sorry. Short-term memory. Memory of Hadil's goldfish. 23.6. Both those are 5 each, and this is 61. Be like about here, right? Then going through, the next one here is 31.5 and 100. So 131.5. So this is 25, 30. So 31 would be like right here, 31.5 and 100 over here. Not perfect, right? I'm actually closer to like 33. Oh well, it's gonna be tough to do this perfectly on my tablet screen. Oops. Uh-oh. Don't drag that. Okay. Next one. 150 and 61.2. So 150 and then up to 61.2. So 60 and then 1.2 right here, right? Going through, and then 260 and 105. 260. This is 200, 250, 260. What was it? 10. I already forgot. 105, sorry. 260, 100. That's roughly what my plot would look like. Now, unfortunately, there is no way that I'm going to be able to draw a very good line of best fit. So what I'm going to do is I'm actually going to circle these dots so that you can clearly see where these dots are. because in trying to draw a straight line with my tablet, this is going to be embarrassingly bad. Actually, there's got to be like a line function, right? Let me just, maybe I can do that. Insert shape. Ooh, let's do a line. Let's see if I start here. No. Okay. Oh, oh. What looks like a decent fit for these guys? Maybe something like that. Look at that. Maybe I can do a line of best fit. Now, keep in mind, do you have to go through every data point? No. In fact, you just have to try and minimize the space between the data points. So even though, like, you can see that this one's a little bit above, or, oh, you can't see which one I'm pointing to. But even though you can see that, like, this data point right here, and that I just kind of highlighted in teal, right? This is like a little above, but over here is also a little above, but here is like a little below, and then like there is almost spot on. I would say that's like a decent best fit line. Does it have to be perfect? No. Now, what do I need to do here though? I need to find basically a slope here. For part 3, it says use the above graph to estimate the value of resistivity of the dose cylinders. So what I want to do here is I want to pick 2 points that are actually on my best fit line. And when I do this, I like to pick points that actually intersect a corner of a box. And I like to spread it out, like one towards my lower values, like down here, where this X is kind of like perfectly on that data point there. And then I'll also pick one of my like higher values, like up. Where does it perfectly go through? Right here, right? I'll put an X there. So I'm going to use those 2 points as my points for my best fit line. And then what I'm going to do is I'm going to say that the slope is equal to the change in Y over the change in X, which in this case is going to be, if I label these 2 points, right? This first point here is, these were by tens. So this is 40, comma, and now I'm leaving off the units for now, just to make this easier. This is 40, comma, 5, 10, 15. So 40, comma, 15. And then up top over here, this data point is, if I go up here, this is 260, 270, 280, 280, 280, comma, what is this? 105, 110. Okay, 105, 110. So as a result, then, I can plug in those values, right? So 280, 110. I don't know why that 110 is following me. Weird. What are you doing, 110? Regardless. So y2 minus y1, so this would be 110 minus 15. This is in units of ohms, over 280 minus 40. And this is in units of meters to the minus 1. By the way, when you divide by meters to the minus 1, it's the same as multiplying by meters. So my end unit should be like the units of resistivity, which is in ohms, or ohms times meters, rather, as expected, right? So ohms times meters should be my answer. Now, let's plug this in. So we have 110 minus 15, which is really just 95, divided by 280 minus 40, which is just 240. And I'm going to get a resistivity of about 0.395, which I guess staying consistent to my like roughly, what would it be, 2 sig figs technically, I would be 0.40 to round this correctly. Ohm meters would be my resistivity value. 0.40 ohm meters. Right? And that's just getting my slope value here. And this is, you might want to indicate this more clearly, that is our resistivity, right? Rho. Maybe I should have boxed that in as well. But that's how we would go about solving that type of problem, right? Finding our slope from our graph. Now it says for part B, yeah, that was only part A. Ugh, this is why this is a 25-minute question. I think I spent most of my 25 minutes right there. There's another group of students perform the experiment as described in part A, but the shape of the dough into long rectangular shapes instead of cylinders. Will this change the affected value of the resistivity determined by the second group of students? Basically, what it's saying is if we don't use cylinders, we use rectangles, will that affect the resistivity? So It will affect the cross-sectional area, but it'll also affect the shape, right? Meaning, Alexia, when we go to find a cross-sectional area and a length, right? The volume of any shape, if you find its cross-section and multiply it by the length or height, right, of the material, you'll have the same volume of material. So you're not changing how much substance you're using, right? You're using the same dough. So as a result, you should not change the resistivity of the material. And another way to briefly justify this is resistivity is inherent to the substance itself. Inherent or is an inherent material property, right? Or is inherent to the substance itself. It describes the ability of the material to allow or to resist the flow of charge. It describes the ability of the material or the substance to resist the flow of charge. Meaning it doesn't really matter how much of the substance you use. As long as you do the same type of experiment, right? The resistivity value should be the same. And then if you really wanted to go into it mathematically, I'm sure you could also describe that you're still using the same volume of the substance. You're just going to have different proportions of cross-sectional area to length. Doesn't matter if it's cylinder shaped or if it's rectangular shaped, right? So because it's the same substance, right, it will not change the value. So same dough, same dough means same row. I can rhyme, right? Same dough, same row. All right. So describe an experimental procedure to determine whether or not the resistivity of the dough cylinders depends on the temperature of the dough. Give enough details so that another student could replicate the experiment as needed. Include a diagram of the experimental setup. Assume equipment usually found in school physics laboratory is available. Oof. All right, what would we do? I guess the issue is how can we accurately measure the temperature of the dough, right? Because what could we do in order to increase the temperature? We can increase the temperature by simply increasing the current, right? Um, and how can we tie this back to the resistance? Well, we still want to measure the resistivity, but how can I measure the resistivity? Hmm. Basically, what we can do is because R, assuming the resistivity remains constant, should be directly related, right? Let's say R is equal to V over I. That might help us. But then I replace this with rho L over A is equal to V over I, right? The reason why I'm thinking about these things is these are things that we can measure. So if we think about resistivity and we think about we can apply like a known voltage and measure the current through it, right? We can set up an ammeter in the circuit, we can set up a voltmeter in the circuit, or we can just measure the voltage coming out of the battery. So using a power supply, we could gradually increase the voltage and then measure in turn the current flowing through the resistor. And that current would be inversely related to the resistance, right? If it forms a linear relationship, what does that mean? That means for direct increases in our voltage, we experience direct increases in our current, right? Ah, this is a bit of a stretch, but I would argue, right, that as we increase the current, we know the temperature of this material is going to increase. What we're trying to do is we're trying to see if, as the temperature increases, we still get the expected resistance value based upon a set rho value. This is tough. Basically, there's a few things that you need to tie in here, right? I'm not going to go through writing this whole thing out because there's different ways to write this. And when I post, and I will post for you guys the solution set of this, just so that you can see like what the AP would look for in your grading. But when you go through this, right, because I know we're running out of time here for today's lecture, and I got to get started with my Regents kids soon. So when you go through this, right, there's a few things that you need to consider. You need to consider a way in which you can relate kind of temperature to resistivity, rho, right? Now, I almost would say that this is not going to be something that you directly do, meaning there's no equation that you've been given to see if T affects rho. So don't think about graphing T and rho. But if we were to experimentally measure the resistance, right, and the current for known set voltage values, right? So we can change the voltage, we can tweak this, we can control this, right? There's an argument to be made that as you have more current flowing through the resistor, you're going to increase its temperature, right? And if you want, you could even have a little probe attached so that as we have more current flowing through, we can notice the increases in temperature. Or basically, as we increase our voltage, right, we're then going to increase our current and hopefully kind of notice that our resistance changes as well. If we notice that for an increase in current or an increase in temperature, so I'm kind of tying these two variables together. Remember, we said the more electrons flowing through a hallway, right, the more collisions that they would have in our analogy way back when. But if we increase the current and we don't see a linear increase in the resistance, because it is technically the same dough, we're going to use the same material, right? We're not going to change the dough at all. We're going to like take a chunk of it, right? Set it up as like a resistor. As we increase the current, we should know that that dough will increase in heat. And if we don't notice a linear relationship between, or really an inverse linear relationship between I and R, right? Then we know that it's not obeying what we'd expect to see for an ohmic device, which means that temperature is affecting its resistivity, meaning its resistance is not constant. So this goes back to, if you remember, and I might have said this a little bit more briefly, that for an ohmic material, if you were to graph V and I, right? So if you remember, R is equal to delta V over I. We could just graph these two things because technically as current increases, right, as I increases, we'd expect T to increase. So as a result, the slope of this thing should equal the resistance of our material. But if it's a non-ohmic device, meaning if basically if its resistance is varying as a result of the change in temperature, we'd actually end up with a different type of curve. Now, I would assume that our resistance would probably get greater as our temperature increases. So we'd probably end up with something like this, where our slope is still our R value, but clearly we have a changing slope or an increasing slope. It might not even be this perfectly curved. It might be some weird shape, depending on the temperature of the material. But effectively, we're going to expect some change that way. So you'd have to design an experiment to first verify, right? You have to verify that increasing the current increases the temperature. I know it's something that we logically expect to happen, but there has to be some double check where you're at least measuring the temperature. And then by changing our I, if I does indeed affect the temperature, right? By changing our I and measuring our voltages, right? We should then see whether or not the slope of this graph changes or whether or not our resistance changes. If it's linear like this, right, for option one, so if it's linear like option one, then that would say that temperature does not have an effect on the resistivity because the resistance varied directly with the current and voltage that was being drawn across it, right? Whereas if it doesn't vary directly, option two, then that means that temperature does indeed change the resistivity of this dough, right? Because our resistance is being changed as the temperature increases. Now I'm predicting that that change will cause this curve because I'm predicting that temperature would increase the resistance of the material. But technically, it could just as equally slope downward if for some weird reason this material had less resistance with higher heat. That's not typical, but depending on the temperature range that you're talking about, could technically happen. So when I say temperature range, I'm really talking about probably more like superconductors in which the curve would be weird, then never mind. But that's okay. That's enough, I think, for you guys to kind of formulate your own response there. Now, your homework is just to write up these two questions. I'm going to stop our recording here.